So during the last lecture we have taken a look how we can manipulate function behavior as well as interact with C++ just from plain C. And today we'll continue on this track by investigating how we can manipulate such behavior in other processes. So for this we'll create a new project. Again, project, a console project. Test. And this will be our target project to modify. We'll let it do something, for example, if message box 3 capital B. Okay, so we have a program that does something. Obviously, it's quite a simple test target. We have already learned how to manipulate a message box, but what we now need to do is to find out how we can do that from another process. So obviously, the first thing to do will be to create this other process. So here, add a new project. We again select console, and then we call it DLL loader, for example. Create. Then we'll set this project as the startup project. Oops. And now if we run it, it will just start the other project. So the first thing, of course, to do is to now start the project that we had before compiled. So before do that, we can set dependencies such that our DLL loader depends on hook test, so that if we change something into in the new project, when we try to run the startup project, it will cause the compiler to rebuild also this dependency. If we wouldn't have done this, when we start DLL loader, it would not automatically build hook test if something changed, which of course is desirable, so that our changes can be quickly applied, and we don't need to press compile on multiple projects manually. So on the DLL loader, of course, include Windows H, and what else we will see later. For now, we need to find a way to somehow start the project. So on Windows, well, there are actually more than one challenges. First of all, we need to know the path of the application to start, and then we will be starting it. And of course, simple and trivial way would be just to write down the path where the thing will be built to, but that's kind of not the smart way. So what we know is that all the binaries will end up in the same folder. So actually what we want is to find out the actual path in which our own process is. So we'll create a t array, my path. There is a there is a previous definition max path, which defined the maximal path length on Windows, 260 characters. Although this limitation is not longer enforced, you can, in fact, using the right path syntax, use on Windows paths up to 32 kilobyte in length, so really extremely long. But many simple Windows applications still just use this 260 character length limitation, so for simplicity we will too. There is a Windows API function get module file name w. So module refers actually to a loaded executable file in memory, and our application itself, our exe file, is a module, but so is any other DLL that the application loads. And on Windows, this, or at least on any reasonably modern Windows, this will always be the ntdll.dll, and other DLLs are strictly speaking optional, but you can expect kernel 32 to be always loaded, on modern systems kernel base as well, and on anything that uses some sort of graphical display, you will also have user32 and possibly GDR32. For our purpose here, we want of course to get the path of our own exe, and the get module file name w is specified such that if we not provide a module handle but just null, it will automatically give us the path for the main module, so the executable file, and not any of the subsequently loaded DLLs. The thing takes three arguments: the module, as already mentioned, which is null, a pointer to the string where to put the path, and then the maximum size. So we can test it quickly. Just need some return. Oops, and that's correct. And we can run it. And voila, as you see, we have retrieved the path as we know it to be correct. Now the only thing we need to do is to switch DLL loader with a hook test. So we can do it in many ways, but the probably simplest one is first to use vcs chr, which finds a character inside of a string from the back. So what we are looking for is just we're looking for the character backslash, which as you might remember, we need to provide two backslashes, since a single backslash starts an escape sequence, and if we just want the actual backslash, then we just put it twice. So this gives us the position of backslash in our string here as an address, as a pointer, and in principle, if we know that this will always work, obviously this function hypothetically might fail, in which case it would not work, but since we here are making more a demo code and not code which you could use safely in production, what we'll do is we'll just dereference this. First we also add 1 to it, because we don't want to overwrite the backslash, and then we just set this to L0. So we kind of truncate the string by writing the terminating null character after the last backslash, and then we will need this path for more than one thing. So first we will create a copy of it. We'll call it let's call the new one exepath, and then we can use vcs-cpy. We should use the S version so that we are well, S stands for safe. The idea is simply that in contrary to the normal string copy, it also takes the max length, so this way we avoid overwriting memory which might not be allocated for our string. Why is it complaining? It wants the size first, apparently. It's complaining. Let's just go to definition of the thingy. So it wants both. So we have destination pointer destination size, source pointer, and max count. That's the N version. We don't want the N version. Okay. The IntelliSense was the problem. It kind of suggests us to use the VCS NCPY, but with the asterisk. But actually, we just want the one without N, because we don't want to just copy a part of a string. We want to copy the whole thing. And this thing here is slightly different. So first it takes the destination, then it takes the length in words, and then it takes, of course, the source. So now it should work and not complain. The N version would allow us to just take a portion of the string, which might sound like a useful thing, because then we kind of would not have to overwrite here, but then we still need to calculate how many characters we want to take, and then just overwriting this with 0 is the simpler approach. Okay, and now we want to append something to the string. There is a VCS cut s. Basically, white string concatenate secure is the full name of the function. This is just like they just use short names, and we provide the destination, again exe path, the length, and then we provide the source. So only the part that will be appended. So in this case, it will be a string which contains the text hook test exe, and when we run it now, our exe path should be the full path to our it's not my path. VCS the R is missing. So VCS CH goes from the left, VCS R, like reverse, goes from the right, and if we forget the right the R, then it doesn't do what we want. Now it works fine. We get the right path. So how do we start a process on Windows? Well, that's quite easy. There is a function, create process W, which takes a few arguments, quite a few actually. So first, of course, the path of the process to be started. Then it takes a command line. Technically, you only need to specify one of those two, and since we don't specify any command line, we just use here null. We could kind of switch those. This will also work. And in principle, you could also start one program with a command line for another program, which for that program might be a bit confusing, but it would be doable. Then you can specify security attributes, which we don't want to. Null. Security attributes for the first thread, also null. Inherits and handles false. That's not relevant for our use case. Creation flags, and this is important. If you remember threads, we could create a thread in a suspended state. Here we can do the same thing. We create it suspended so that it's created but doesn't do anything. Environment. Environment is pretty much if you open any command window, well, not this one, like a normal old school one, not this partial shit, and then you set, then you get a whole list of defined environment variables, and all those variables, in principle, you could provide here your own list of them to be used for the process, but we just say null, and then the Windows will just create a default environment as it did here for CMDexe, which we started with all the default values. Okay, next thing is current directory. So we could specify a working directory. This is something that especially on DOS was kind of very meaningful. On Windows, and it still kind of is, because it's in a way a succession of how you are using things. The idea is that if you have a working directory, that you can then access files in this directory just by providing the name. No, you don't need to provide the whole path. And this is also relevant, for example, when looking for DLLs to load and so on. But modern applications, aside of these low-level functions, which are usually abstracted from your away anyways, don't use this. When we just create it as like this, it will just create with the same current directory as the parent process, which in case of Visual Studio will be again the directory where the solution file lies. You can actually configure this, I think, debug. Working directory, project directory. So here you can specify from which directory your program, when you are debugging it, will be started. Obviously, when you start it manually, then it will be started from wherever you have started it. But here we specify null since we don't care. And then we have two more things to specify: a startup info W and a process info, both as pointers. So we need to create those. startup info v se is equals, just initialize everything to 0. The thing has quite many members. Actually, we can just go there. So if you are creating a graphical application, you can specify on which desktop it will be shown. You can specify the window title to be used unless the application overrides that. You can specify the position where it should be created, some additional flags. If the window should be shown, minimized, etc., etc. And you could specify pipe handles if you want to intercept console input, output, or error messages. But for our application, we don't care for any of those, so we just leave everything at 0. And here we pass the reference to it, so the pointer se, comma, and the next one is the process info. Information. This one is not w. The thing is, here this is a white string, and if you would have an ASCII string, then this would be just LPC CSTR. So there are two versions of this structure. Of the process info, there is only one version because it doesn't contain any strings. It just has handles and IDs. So PE, we also initialize this with 0. And while SE won't be altered, PE will be. It will receive a handle to the first created thread in the process and the process itself, as well as the IDs of those two elements, objects in the system. And a process on Windows cannot exist without a thread, so as soon as the last thread terminates, the process is terminated. There is no... those states are kind of linked together on the kernel level. Okay, and at this level it would already start our process, but there are a few things we need to take care. First of all, we would want the program to actually run, so we need to resume thread. On Windows there is a function also suspend and resume process, but internally it just enumerates all threads and calls suspend or resume on each thread. So it's not like you could suspend a whole process in one atomic operation. There are on modern Windows like 8 and 10 other methods called process freezing, which can be used in a similar way, but they work a bit differently, and we won't be looking into them. Just know that if you would use suspend or resume process, it would not suspend everything instantly, but like one thread at a time, which for most cases is good anyways. And of course the last thing we need to do is to close handle. Since we have received two new handles, we need to close them. Obviously, since we terminate, we kind of could say, meh, we don't care, the system will do it for us if our process ends. But since we want to demonstrate how to do things properly, and it's very likely that you might want to create a process in one of your applications that you write later in your career, and maybe you want to start an application once per minute and have your parent process to run for a day or however long your measurement takes. So in this case, you would obviously not want to leak a process and handle handles. So it's important to know which things you need to dispose of manually once you have obtained them. So now we will just test it. We will just run the thing, and we will see our program started. It started the other program. Our program already terminated, in fact, so this thing already shows that nothing runs, but our started program, of course, is still doing its thing. In this case, I said yes, so it terminated. So our goal will be to override the message box function like we did in the function hooking example, just that we want to do it from another process. And there are many ways how one can achieve such a thing. And they can be arbitrarily complicated, but since we want to be kind of efficient with what we are doing, we will try to use a rather simple, or maybe not simple, but a rather straightforward approach, which means we instead of rewriting just the target process and doing everything by hand, we will try to minimize the amount of code we need to write ourselves on the assembler level, and we will create a DLL, so a module which can be loaded by the other program, and then we will just force the other program to load that module. And the module, since itself it is just a normal C++ or C program at your discretion, you can use your compiler, you can write normal C code, you don't need to do anything in assembler. Later we will also try a more advanced injection method, but for the first demo we will just use a simple DLL and don't write any own shellcode. So the process generally is called a DLL injection. And for this we obviously need a DLL. So let's create one. Add new project. DLL. The dynamically linked library. We just could also to create this one. It doesn't matter. Now we just create an empty one. Yeah. We'll call it hook DLL. Okay, the thing is created. It's, as you see, quite simple. It created for us a few more files, but basically we just have a few headers, which well, we have the Windows header here included, but we don't really need much of it. The other one just includes the first one, so it's also quite trivial. The file here is just for the precompiled header to be used, so we don't care for this either. And in the DLL main, we have our DLL main function, which kind of acts as an entry point of the module. Although the thing with modules is that what they do is they export functions which then can be called by the program that loaded them. But the way Windows was designed is that as soon as a DLL gets loaded into a process, it has the opportunity to do something. So it can initialize some internal states. It's not everything is just left to the program which is loading it. So this kind of acts as an entry point, but it's not really just an entry point. It is called multiple times. When we go back to our hook test process, it's quite trivial. We have the main, and when the program starts, we start at main, or at least our code starts. There are things that happened before, as I think I showed you at the beginning in the stack tray. So everything starts in the NTDLL, then it loads this some things, and then it runs the C runtime startup code, which is generated by the compiler, and then at some point the main function actually is invoked. So there are a few things that have happened before, but this only happens once, and once your program, all of its threads terminates, the program terminates with a DLL. And the DLL main is called basically for each of those reasons. So process attach is when the program, when the DLL is loaded into a program. This will be called with this reason. If your program terminates, or rather if your program unloads a DLL, the process detach is invoked. So the idea is that if you load the DLL and then unload it, the DLL could instantiate something, allocate some memory for some internal operations, and then once you unload it, it will be notified about it so that it can release those resources and not create a resource leak. But it's actually more complicated, because for each time a thread in your application is created, this DLL main is also invoked, like this thread attach and thread detach. So this is thread creation and thread destruction. And the idea is that you might, in certain scenarios, want to keep a state per thread. An example of such a per thread state might be, for example, the get last error function, which I think I mentioned when we were looking in the different Windows APIs and thread synchronization. So this would be an example of a persistent state, although it's not quite the same thing, because this is persisted in internal structures created by Windows for the thread automatically. Here you only get the opportunity to create something that behaves similarly for whatever your own DLL functions would be, and of course to ensure that you always clean it up, which is quite useful. In principle, the process detach and attach, this you could actually do manually. You could just load the DLL, and then you once you loaded it, then you call a function to initialize it, and before you unload the DLL, you call a function to uninitialize it. So automating this process is not really necessary. But with threads it's different, because in your application you will not have something that would allow you to hook this easily in any other way. So of course, so if you want to more simply be able to create and track and then destroy a thread per thread persistent state, this is quite a useful method. For our case, we will only care for this process attach, and we can already create our DLL content. So go to our function hooking. We just grab everything until here. We already have Windows included, so this is fine. we will need to rename the one function here to install hooks. I think install has double L. Technically it's install hook because we only have one, but we could also, if you hook more than one thing, we could call it install hooks, and then we just call it from here. There is of course a let's call it catch-22 in this scenario. That is technically, if we are getting unloaded, we need to uninstall the hook. So if we want this, we could later look into restoring the original message box function. So we had made a backup, I think, here, but we didn't use the backup later on. So we could actually create a unhook procedure, but this is something for later. Usually in these scenarios, we just load the DLL and then we just leave it in. Given the amount of memory modern system have, a small few kilobyte DLL is really meaningless in the big picture. Okay, so this DLL is already kind of serviceable. What we of course should do is again set up project dependencies. We will set that our DLL loader depends on the hook test and the DLL. We will of course need the path to this DLL so that we can load it. So here we will quickly create a new copy. DLL path, hook DLL DLL, hook DLL.DLL. And before we actually inject it from outside into the program, since we control the test program, our test target here, what we could do is actually we could just simply load the DLL and see if it does what we want it to do. So W, and the thing is that it takes the current working directory, the path, and the own directory where the thing lives. So if we now load L, then it should be able to actually load it without us to have to specify the whole path. And here of course we put here there a breakpoint so that we enter here. So let's run it. We have a warning and we have an error. This we don't care, and this needs to return a value. We don't want that, so we just make this void. Now it builds it. And I forgot a breakpoint. So obviously we don't see what we are doing with the breakpoint. We put a breakpoint here, and then so at this point the process is created but doesn't run, and then we can debug, attach to process, hook target, and we can attach to it with our debugger. And then if we continue, then we arrive at a breakpoint. We can load here the symbols, but this is just a default debugger breakpoint in the NTDLL, which is always triggered if you attach early enough. The idea for this is that it gives you the opportunity to then set up other breakpoints before the program actually continues. So let's just continue, and as you see here, we are now loading our DLL. So in the stack trace here we are at main, load library v, which then calls kernel base, which then calls NTDLL, which then loads the DLL, and at some point calls this entry point. Technically, this entry point wrapper provided by the C runtime, which then only at some does some other things, and then only at some point calls our own main. It's kind of like with the main of the program. It's kind of here, but in reality there are quite a few other things compiled into the process that are executed first after the other components have already gave us the control to our process. Okay. So here we have all the symbols loaded, so we see the whole call stack, so we can terminate this. Apparently the thing here is not doing anything, which kind of makes sense since we did not adapt our hook yet to what we actually wanted to do. So let's see, we want this question to be automatically answered with no. Okay, so that should already be one fix. And you see we already don't get the question, just get the up arrows. So now we will also add something to suppress those. where was it? Hook test. Let's pin this so that I can easier find it. In principle, we could just go with everything that has title warning. That's a bit of a more broad tag, but why not? Oops, that was the wrong one. I wanted to paste it here. Default is okay. So now if you run it, we just get app runs fine, and all the other message boxes are suppressed. So we know our DLL is good. Now we need to find out a way how we can inject it without any cooperation from the target application. And this is possible on Windows in quite a few ways. So I prepared some examples for at least 3 methods, and then we will see how far we go. So how much time we have. Let's start with the first one. It's like the most classical one. It is called the create remote thread approach. There is a Windows in Windows there is a API function that allows a process to create an own thread in any other process it is permitted to access. So maybe before we start here, so that you are not too worried about your own security on Windows, each application each process runs with under a certain user, which is identified by the user token. It can be you as well. If you start something as administrator, then it will be also you, but it will be so you have here elevated yes, and you have when you go to is it general groups administrator, it's enabled. If you have something that isn't where it's still you, but you don't have administrative privileges, then you see that the group administrators, it's present on the token, but it's disabled. So you don't have the privileges if you run normally that you would have even though you are a member of the administrator group. And also the owner here changes as well. So and then of course you have other users on your system, like the system itself. So any system service runs as anti-authority system, and some network services also run like under special service accounts, but most like that to local services and network services. And system, those are the 3 that you typically have on any Windows system. Others are only used from time to time, like the trusted installer, for example. And the idea is that each of these tokens identifies a user with certain privileges, and processes are protected such that only processes belonging to the same user can access each other, except of course if the user is an administrator. An administrator can access system processes of other administrators, and processes of other users. So obviously that's why you not grant admin privileges to applications you don't trust. And so generally on your system such restrictions exist. We can take a look here, for example, into the permissions. So for example, this process which was started as an administrator, only system has full access, everyone in the group administrators has full access, and there is very limited access to the current login session, but only query information. So you cannot change anything with that, and you can read some memory, which might not ideally be great. You can terminate, but you cannot write memory, you cannot do other things, you don't have full control. While on the normal process, for example this one, when we look on permissions, you have, well, the system always is allowed to do anything. It has log current session usually as well, but here you have then your own normal user, not the administrator group, and here you see that everything that runs under your local user has full access to everything with regard to this process. So on Windows, in this sense, applications are quite vulnerable. There are methods how such things are mitigated. For example, we have here a web browser open, and where is it? Chrome, and you will see here that so let's see. We have here they are chronologically sorted. So the one at the bottom is like the real the first one that started, and then if we continue, for some of the Chrome child process we see still more or less similar permissions. So we already here see that some things were dropped, but then if we go further, you see that some of them run under a different user ID. They're still owned by you, but the actual user is well, not a real user, it's a app package. This one runs on the normal one, The other ones also run at the normal one. Well, if you... And the idea is generally that the most vulnerable process, where the biggest risk that some expert on the website might take them over, they will be run under such a pseudo user. It's called a restricted token. And even if they, whatever malicious code gets into such a process, that could take over the whole process, they won't have your permissions to access any of your other applications. So if, for example, if you open just Notepad and write there some secret text, any other process within your user account that runs with your privileges can read it. It's not great, but that's how Windows always worked, and I don't see this changing anytime soon. So that much to this. But as said, usually things that are exposed to external threats should be run in such under such restricted tokens, so you should be secure enough. If you don't feel secure enough, you can Google for various open source software to protect your privacy and isolate things on your computer even better. But that's outside of the topic of this subject. So this let's create our function. So pull inject DLL DLL thread, just give it some name, and we specify our process information as a reference, and we specify the path to our DLL. Const DLL stern. This will be generally the function prototype for all the different methods that we'll be using, and it's not super straightforward how to use it, because the way it works is well, let's start it. So we have handler thread create remote thread. We need to specify the program, so we use our pi process handle, and then we have different things to specify. First of all, security attributes, again null. That means that it will create default, stack size default, start address, and that's the first difficulty. We need an address of a function inside the other process which we can actually call. And if we don't know much about the other process, obviously we don't know an address, and one might think there probably won't be a function that will do whatever we want. But luckily, the way Windows is implemented, the kernel32 DLL, which is loaded by almost all processes, has this load library W, which we have used before. And the way address space randomization works on Windows is that when a DLL is loaded for the first time, it will get a random base address. But if any other application loads subsequently the same DLL during the same session, the addresses will be the same. So in our program, we know all the addresses of all the system libraries and can rely on those being the same in other processes, with very edge case scenarios where that might be a on purpose broken by the other application. But it's highly unlikely. So just to get the address, we can go with void asterisk array is equals W, and we already have the address, so we provide this address as our target. We just need to cast it to the right type. Oops, that was the wrong thingy. LP start routine, comma. Then we can specify one argument, and this is where the property of load library W comes into play, that it actually just takes one argument. Because if it would need two arguments, especially if like the first one would be not so important, but the second or third one would be important, we already couldn't use it. But since it actually takes just one, we can just give it one. But what does it want? Well, if we look back to the function here, what it wants is the path of the DLL to be loaded, an address to the path, to be more exact, an address to the string which contains the path to DLL, to be perfectly exact. But since our application has their own memory address space, as you might remember from the memory management lecture, then the target process, then we cannot easily offer any of our own strings to the other process to use. So when I say we can create our own thread in another process, it might have been a bit over-exaggerated. We can create a thread in another process, but it won't be in any way connected with us. So how do we work this around? Well, you can, using other Windows functions, allocate memory in another process, get the address inside the other process, and then use another Windows function to write at the specified address into the other process. So let's do that. First, of course, we need to know how long this memory block should be. So size t len is equals, let's say as len of DLL path plus 1 and times size of wchar. So we have the length. Now void address virtual alloc x. Virtual alloc you might already remember, but virtual alloc x extended allows us also to specify in which process to allocate. While the normal virtual alloc just allocates where we are, we can specify an address for which we don't care. So we just got to say null. It will then pick an address for us. We specify the length, so how much memory we want, and then of course allocation type and protection. So we go with mem commit and page read write. It doesn't need to be executable, it is just a string, and then the process memory. Again, we need to specify the handle to the process, which must have the right permissions open. Then we specify the address, so address. Then we specify what do we want to write, so this will be our buffer. The size to write, which will be again length. And we could specify a variable which will receive the amount of bytes written. In case we want to write more than was available memory at that position, the operation can crash prematurely and tell us that it only half complete, but we don't care for that. We want it all or nothing, so we just say null. And at this point, we can use this address as the argument for our thread. Creation flags, let's again go with create suspend. But we could in principle not do that, and we don't care for the actual ID of the thread. We just care for resuming it. We could in principle have a check whether that succeeded or not. So here, if this is equals invalid and value, then we could return false, just a sanity check, and then maybe we would like to wait for the thread to finish its work. So for single object thread comma infinite. Okay. And we of course should not forget to close handle h thread. Okay. And once this thing is done, it will resume the main thread and our modification should be in place. So let's try if it works. I did not. Now the question is why it did fail. So first of all, of course, we can put here a breakpoint to see if everything went fine until this, and it did not. Wait, did we not call it? Oh, we forgot to call that function. That's a very good reason for it not to work. So we want pi and DLL path. Suck. Okay, let's run it now. Do you see it's already working and doing its thing. Now, this is of course a simple and nice method. In principle, you can do such a thing also once the program is already running and doing things, but then again you would need to ensure that your hooking mechanism will not trigger some race condition and cause a crash. So it's safer to do your modification before the other process actually starts doing its own thing. But in principle, as said, this can be done at any time. Now, there are of course other methods how you can achieve the same thing. So let's take a look into another one, which is called a asynchronous procedure call. We steal the function prototype here. We just call it DLL. What do we call it? Let's call it user RPC. APC. The asynchronous procedure call is APC. So it will be somewhat similar. We of course again will need to allocate some memory in the target process and put the string there so that we know so that it knows what to do. Then we can also use the load library, but we'll use a different function to make this function be executed. So here, as said, we are creating an on thread which will do something. Here we are querying queuing a user mode asynchronous procedure call, and the idea is that it can be queued to a selected thread. So the thread which we queue it to must already exist, and this thread it will not be like interrupted at any point in time when we just give it to it, because that might break things. But the thread has to be in a alertable waiting state. For example, if you use sleep X, this works. If you just use sleep, it does not. And there is a whole list of Windows functions which put a thread into an alertable state. And here we are basically just gambling on the thread getting into such an alertable state before it passes control to the main function as a part of its internal initialization routines. So okay, is equals PC, Q user APC, and there we specify the target function APC func, which will be again our load library target, because it's do I have a typo? I think that first PAPC func load library. Then we can again specify the thread where to queue it to. So PE thread, the only thread which exists in the process at this point in time, and then we can again specify an argument along ptr and blah. And then if this says okay, then it's okay. Oops. The idea with two exclamation marks is just to turn a bool, which technically is just an int, into an actual boolean. But in principle, since we are returning, this is kind of obsolete. But let's do it anyway. So suck. We provide the same things in the brackets. Okay, let's run it, and voila, this works fine as well. So what we also can do, of course, now is we can put a breakpoint here, run the thing, then debug attach to process, hook test, and then go to our DLL main. I already have the breakpoint, so let's run it. We have one debug breakpoint, and then we reach this, and then here we see in the call stack how the thing behaves. So inside of the NTDLL there is a NT-test-alert, a function which tests whether the APC is queued, and if there is one queued, then it will be executed, which then brings us to our DLL's main function, which then modifies the target process. These methods are generally the simpler ones. They all rely on this load library W being already available, which, as mentioned, usually it is available very early, but this you might want to create some injection mechanism which would not rely on any other DLL than the NTDLL itself. But there you don't have a function like this load library W. You have a LDR load DLL, but it takes 3 arguments, and the first argument is actually reserved at always 0, which is kind of in our case useless because we cannot provide any other arguments here. So we need to find a way how we could make this work, and we can do it in a very advanced way. It's called writing own shellcode. So what we will do is basically we will overwrite not just a path to the memory of the other process, but we will actually write executable code, our own function, into the other process, and our own function inside the other process's memory will then invoke the right libraries, rather the right functions to load our injection library. In principle, if you would want to write much more handmade code, we could make our shellcode do everything, but this is kind of much more difficult and much less easy to debug, as we will see here with the simple shellcode that we will try to write now. So unless you want your modification to be really stealthy, then you just load the DLL and it's simple. And the other point, so there are a few things to the shellcode. First of all, some initial shellcode you will need to write in assembler by hand, but you could create the mechanism such that it would then hand off to a code which you could compile as a DLL, but then just in one go drop into the other process's memory, like without invoking any DLL loader routine. This is not straightforward, because normally the DLLs, when they are created, they are not fully position independent. So when they are loaded, there is a list of addresses inside the DLL which needs to be adapted to work with the right addresses. If you only drop your code section into another process memory, these things will not work. And one of the things that it breaks, for example, are strings like this. So what you can do is you can initialize a string like a comma b and so on, but as soon as you try to initialize it like with a nice string in a nice way, then this will create already position dependent code. And so there are quite some limitations to this. And the other issue is that you cannot put breakpoints easily in Visual Studio on your shellcode, because what you would want, of course, for good debugging is to be able to go in your C code, put a breakpoint, and then have a breakpoint there. But if you're load in such a rogue way your code into a process, then for the debugger, it will see that that's code. You will be able to put a breakpoint by address, but it will not be able to create the connection that this code actually corresponds to a DLL that you have wrote to which you have the PDB file and the C file. If you would use a different debugger like WinDBG, you could in principle specify manually that some address range is a base address for a given DLL for which you have the necessary data, but that would be far outside of the scope of this lecture, so we will not be doing that. Yeah, and so there are limitations to this approach, and if you can avoid it, just try to avoid it. That's the easiest really way. The most convenient way is just to have a DLL which you load and then it does its thing. So without further ado, let's start with that. So again, we copy our initial function and we will give it a name. How do we call it? Let's call it hack thread. Yeah, that sounds good. Hijack thread. Zack. The function. It takes the same arguments. You can call it instead of this. And once you write your own shellcode to another process, you have a few ways how you can invoke it. Will be for now just using one of those. But in principle, it can be done in many ways. So first, let's just implement this function. It will rely on a second function which we need to write in a second. But our idea for this hijack thread is that we will. So as you remember, we already have one thread created, and the thread thinks that it should enter execution at the address of the actual entry point of our main test program. But in reality, we can write a different value to the thread context and then tell the thread to start with our code, which only once it's done will then invoke the actual real original entry point, for example. So there is the structure context ctx context flags is equals context control and for okay get thread context. Again, then we need the thread pi.thread, comma context will be a reference to our context. We don't care for an error. We don't care for any other thing for the moment. Then we will, then we'll, actually we should test it. So if this is false, if not that, then return false. Okay. Then we'll do something. Don't matter. This, whatever we do here, will give us an address which we can then write to ctx RIP, so the instruction pointer, but now we don't have it, so let's comment it out. And then, okay, it's like set thread context, and then the same arguments as before. Oops. And this is malformatted. And we write, okay, capital letters. And that's pretty much it. Then we just for symmetry, let's just go with this approach instead. True. So at this point it appears pretty easy, but of course the right shell context function will be everything but. So as you might remember, we have this online disassembler. Not this one. Is it this one? No, that's the shitty one. That's a good one. So let's grab the link, write it down, because we will be using it a lot. Okay, so void asterisk, write shellcode. What do we need? We need handler age process. We need let's call it return address. So this will be the original address to which we want to jump. Once we are done, then we have our DLL path. And the other things we can do later. For now, we just go with the simplest version of the thing. Let's be small. Okay, let's use it. I mean, it doesn't do anything, but let's use it anyways. So it will return to us the address where the RIP should point to. It takes payee process because it needs to access it, and it takes this address, the original value of this address, because it will at the end have a jump to there. And of course we need the path as well. Good. So let's see, what do we need? We will need some memory, of course, in our target process. So size t DLL path size is equals, we already had this here, but the path size. Then we want some addresses, so void asterisk LDR, the DLL. That's the DLL load function of the anti-DLL demo low level one. Get procedure address, get tool handle W, L anti-DLL.DLL. The get module handle gives us the same thing back as load library W, but only if the module is already loaded. So it's better. Plus, load library increments a counter on the library. So if you load library, then you need to free library the same amount of times as you called load library. The get module handle W doesn't increment anything. It just gives us the base address if the thing was loaded or null otherwise. With other DLLs, of course, we cannot rely on them being present, but with the anti-DLL on any system released in the last 30 years, which is reasonably new. So basically everything that is not Windows 98, 95 or Millennium, we can rely on the NTDLL being present. It was introduced in the first Windows NT, which was released, I think alongside, or at least close time-wise, to the Windows 95. It basically, after Windows 3.11, you had two successors. One was the Windows New Technology NT, and the other was the Windows 95 that you might have seen already at some point. Okay, so here we need, of course, the name of the function, LDL, DLL. And you might notice that here we are providing a wide string, right here we are providing a narrow string. So DLL, function names are always just ASCII names, while a path can be a wide string. Although we could also just use the get module and handle a to use here a ASCII string as well. Yeah. So for now, this is all we need here. So we have a size. Okay. So we will generate some shellcode first, and then we will write it to the target process. With modern x64 architecture, it is quite nice in as far as that we can quite easily generate position-independent code. With the old 32-bit version of the x86 instruction set, that was a bit more challenging. So for now, let's write our shellcode. So we will need some pointer with data ptr. So we will need, we will want to have a data segment. Data size, which will contain, for example, so we don't want like to have the string in one place and then the shellcode. We want to have like one code block which contains the shellcode and the data and everything needed, so that everything is nicely self-contained. And to reference this, we'll use this 2 point information, and then of course we'll have a buffer byte my shellcode. Let's allocate a page for it. So a kilobyte should be more than enough. We null everything. Okay. So let's think about how we want the whole thing, let's say, to be structured. So assuming we want to jump in at the very beginning of our shellcode, so let's write a comment to describe our plans. So first at 0 we would have our jump to main code. Then we would have some data around which we are jumping, some more data, and then at some point we have our main code which does something, and then we are done. I call it finish code, and the idea is that the finish code will be the code part which will which does jump to return address, and this maybe we should let's just call it like this. That makes sense. Okay, to write the shellcode, we'll be again using this helper thingy, which I have shown you already once. It's really nice. Zack. Copy it, we put it here. We initialize it, code .pb is equals our buffer. Okay. Good. So let's introduce a few more pointers which we'll need. DLL path ptr, that will point to the address of our DLL path. And we will need a finish pointer. This is for now 0. Okay. So beginning of our code. So first thing, which is nice to have, since as you might remember, I said we cannot set a breakpoint in Visual Studio. What we can do is we can hardcode a breakpoint into our code. 0xcc is a int3 instruction. which is a debug breakpoint. And in fact, Visual Studio uses such instructions to set its own breakpoint. So basically, you tell it to set a breakpoint somewhere, and what it does basically is it overrides the original machine code at this position with a int3, and when this is triggered, then it overwrites it with the right code, makes a single step, then overwrites it back with a int3, and then resumes the execution. So it's a bit convoluted, but it works. And since we might want everything to keep the right offsets, we can also write a no operation. It's 090, but we'll at each point always only enable one of those. So let's make maybe hash if one else hash else. The idea is that we don't shift the code when we switch between having the breakpoint and not. The no operation is a code which just does nothing. It just is there, and the processor just runs over it without changing anything in memory. Good. So now stress code pb++. We want to jump. Jump is 0xe9 to some address. Jmp x. Let's write some value, and we can. The way I came up with these numbers is I just write my assembler code. Go to the online assembler. 64-bit inline suck, and the thing spits me out. In this case, it says EB. In E9 should also work. What's the difference? Let me think for a second. E9. Yes, yeah. Disassemble. Zack. Right, and then we need an address where we want to jump. Yeah, E9 is a 32-bit jump, while this one here, when we just use jump, created a very short range jump, which we don't want. So we would here just A, B, B, C, C, D, D, so that we force the length we want. And then if we build it, we see that we have just the E9. It modifies the value slightly by an offset, but we don't care for that. And then we have, except for this modification of the address, we just have a 32-bit number. So this number we want to save. P P data size. For now, we want this to be code.pd double word, so it's a 32-bit number plus plus. So we get the address and advance our pointer to the next thing. And we can of course here write down where we are. We are at 1. Here we will be at 6. Since we have 1 and 4, that's 5, so we are at 6. Now let's maybe add some more knobs, just that we have a nice alignment. Here we are at 8. So the thing is, we want to avoid data misalignment issues, and for our data block, we want everything to be aligned to the 8-byte boundary. So okay, good. Then we have our data ptr is equals code.pb. So we want to save this address, and then we can start writing our data section. So I will just call it plus 0, because it will basically be whatever is our starting offset plus 0. So we are counting again. Ulong data pos is equals 0. So we need some count again. and const long return address offset is equals data position. So this will be, well, at 0, but I will try to keep the things look in, let's say, this similarly, so that it's easy to adapt it to other things. And then of course we want to write something here with this count. So let's just code let's say keyword plus plus is equals right. First we need a cast int 64 get our return address. Okay. Yeah, so now we are at plus 8. Now we want the address of our load DLL, so const long LDR DLL offset ist gleich datapos plus 8, and this thing gets the address assigned. Zack. Oops. Plus 16. Good. We need something more. We need one more thing. Let's shift this. Plus 16. This will be bigger. We will see what it will be. So the way this function is defined, let's quickly check. This one is, so first is a path optional, which for us it will be null because the thing is not really used. Flags will be null, and here we need a pointer to a Unicode string. And a Unicode string is something that's defined in one of the Windows headers, which will include hash include internal .h include. Let's jump to it. So you have a length, you have then a max length, and then you have some padding, and then you have a buffer pointer. And all the NTDLL functions take this sort of strings instead of the zero terminated C style strings, which kind of is reasonable, but complicates things for us because we need to create such a string in memory. So we will do that now for our DLL path. Obviously we still need the the DLL path itself, the return address. So although we could maybe first here go with our load DLL because we need it anyways, then we are at 16, and now we will create our Dingsbumster Unicode string. So at plus 16 const long DLL path set is like data pointer. Oops, data pointer data plus 16, since the whole thing is bigger. There's a buffer and some other data, and asterisk code.pp word plus plus is equals the path size, but I think it's wrong. Yeah, we need to remove the +1. We want really just the length, not including the terminating 0. Then the max size, which is plus of oops, because this is with the terminating 0, although it doesn't need to be, it could be also without it. We can just quickly write down Unicode string 64. Max. Oops. Length should be written not capitalized. Then there will be the mentioned padding because of data alignment. And then we will have the buffer. Pad ptr is equals. So we saved this address. We've already prepared this here because we'll be writing it to it later. Code 0q plus. So we take the address, we save the address, and then advance the whole thing. So now we should be at 32. Okay, and then of course here it will be the buffer. Okay, we're at 32. And now we will need some dynamic data, so things which will be generated, which will be populated, data which will be populated during the execution of our code. Although technically, yeah, it looks like it's not needed because we won't do anything with this value later on, at least not in the first iteration of the code. But the loader load DLL function requires this to be available. So if we provide null, it would provide null here for the handle, then it would crash. So we need to, or it would return us an invalid argument. That could also happen. I'm not sure which one it does. I think it will say invalid argument const long the LL base offset is equals our data ptr. Zack, data plus equals 8 because that's just one pointer, and asterisk code pq plus plus is just equals 0. So here we don't write any values yet. Good. And now we are at plus 40. And for now this should be enough. Okay, so let's create a helper definition. Let's define database. This code snippet gives us the position of the start of the data section relative to the current instruction pointer value. So code pb minus data ptr code pb minus data ptr, yeah. Wait, that's needs a space here. This we need to negate, not to negate, to make it negative. And then we need to subtract Caesar of word from it. And that should be it. Good. So let's write label main code. So this will be the main code which we'll be working with. So we also will need the data offset first. So int64 data offset is equals code pb minus my shellcode. So that's the offset of where the thing ends. And we will write this into, we have saved here data size somewhere. can now here into data size with a small modification. That is, so asterisk data size is equals data offset minus byte stern per data size. Take the address itself minus mysc plus diese of Coulomb. Oops, small s. Okay. This we'll need later. And now we will start with our main code. So first thing we want to do will be to save all the registers of the CPU to the stack, so that whatever we do will not change in the end the status, the context of the thread, so that once we are done we can undo all the visible changes so that the thread can resume as if nothing would have happened. So save all CPU registers. To save the FPU registers, code it's quite easy. Just use the 0x9c push fq opcode. It just pushes all of them on the stack, and that's it. For the other ones, for the integer registers, it's a bit more difficult because we don't want to save one of them, and we need to use different save instructions depending on whether they are 32 or 64-bit registers. So for int e is equals 0, we write a code which will write code. E is less than 0x0f, so it's less than, it goes through all the possible register numbers. As you remember, there are 16 integer registers in the CPU. Well, in a x86 64 CPU to be exact. Okay, so first of all, if e is equals 0x04, then we just continue. Semicolon. Keep saving RSP. We don't want to mess with the stack pointer register. And if e is larger than 7, then we need to add the prefix. So asterisk code punct pb++ is equals 0x41, comma, okay, and then the normal save instruction, asterisk code, code punct pb++ is equals 0x50 or I and 0x07. This should be an I. Right. So basically the save instructions for the lower 8 registers are like 50, 51, 52, 53 until 57. And if we want to go further, then we add this prefix and then start again at 0x50. So this will save all the registers except for the RSP register, and it creates a push r asterisk register. So our IP, our RIP is a different one, it doesn't count here. RAX, RBX, RCX, RDX, R8, R9, and then the higher order ones as well. Okay, so we saved everything. Now what we want to do, since we will be calling functions, we want to reserve some space on the stack so that we have enough stack available. So reserve, how much do we need? I think 4 plus 3 q1 on the stack. This will be a sub RSP, comma 0x38, and let's see what that is. Zack. Okay, this gives us the code that we want. Asterisk code punct pd++ equals null x 38 c 8348 Yeah. Then we need to prepare the arguments for LTR load DLL, because we will be calling it. So first we prepared the stack, now we prepare the arguments. As you might remember, the stack needs to be 64-bit aligned, and it will save the first four registers. At least it wants to have enough space to save the first 4 registers to the stack. So that's why the 4 here. And the +3 is for alignment, because what we want is that once the call puts its return address on the stack, that then everything will be correctly aligned. So that's that. So we have here our load DLL. In principle, since the thing only has 4 arguments, we don't need to put any arguments directly on the stack, which is nice. But it would not be difficult either. So let's see what we want to do. First we want move RCX 0. Then we want move RDX 0. Then we want RAD address layer R8, comma, and what we basically want is here the DLL. Let's write it differently. RIP RIP plus DLL base offset. Is that the correct? Or was it the other way around? No, first the string, then the handler. So first is DLL path. Sorry. DLL path offset, which is here. DLL path offset is the Unicode string, right? And then we repeat the same thing, but with R9 and with the DLL base offset. So we take this, go here, we feed it some, that's the wrong one, we feed it plus something that we will be able to recognize as a pattern, and here we have it. So it's 3 opcodes and then our double word. So it's 1 opcode, but it's 3 byte at our double word. But before we do that, we need this here as well. So zack. Okay, and if we change this RDX, you can observe this, and only one value will change here. C1 changed to C2. So let's first write those down. Asterisk code punct payword plus plus is equal 0x C7 4 8. Punkt pb plus pb plus plus is equal 0x C1, and then the double word comes punkt pd plus plus is equal 0. The other one is the same, just with a C2 here, and those we already had before. Code punkt pv plus plus is equal 0x8d 4c semicolon, then pb plus plus is equal 0x0d, and then again the p is missing, a double word but not 0, but instead it will be our database minus DLL path offset. So what this calculates us, so what this calculates us is the relative offset from wherever here is to wherever this lies. So that's how this operates, and then we repeat that thing just with a slight modification. It's here is sorry, this should be 5, and this should be D. So that's for the R8, and D is for R9. And then we have here, of course, our DLL base. Okay, and last thing to do will be to call our function. So call at the address RIP plus how did we call it? Yeah, that's how we called it. And it will look the same. Call run. Okay, so ff15 and then the address. So it will be a bit shorter. 15 ff, and then the address should you wrote down here. Right. Okay. So we have loaded the DLL, and at this point it will already have triggered our load DLL. So at this point, kind of, we are already done with the initial part of our code injection. Now we just need to repair things so that we can resume the execution of the original program. Finish code. Code. As you see here, finish code is not even needed as a label. We just continue from where we left off. But we will save it, since for later we might want to make it more complicated. So finish .ptr. We save this. Asterisk is equals word code pb minus with the asterisk per finish minus size of word. So we save this for later, and now what we basically need is we need to undo this. So not so bad add. That's asterisk code .pd++ is equals 0x. Let's see. Okay. 0x 38648348 8 8 4 8 sorry for 8 8 3 C4 3 8, yeah, correct. And then we undo the other thing. So we grab our loop, just that we change here to 58, and the rest remains unchanged. And then we just missing one more thing to do this. Of course, this is then pop, and this will be skip restoring, and this will be, of course, our show pop, and pop is 9D. Okay, so at this point we have restored everything that might have been broken, and only now we need to jump here to mp to RIP plus our original return address. Zack. Oops. Okay, so it's FF25 and the address. So address code .pb++ is equals 0x25ff, and address code.pd++ is equals database plus this, and we are done. At this point the application should resume its execution, and there is nothing more to do. It is customary in such cases, once we are done, to write some just a tailing breakpoint 0xcc just in case, so that we know where the thing ends, and cc is easy to spot, so it's nice. And now, of course, one thing we forgot, or rather not forgot but omitted, this thing is yet constructed in our memory. Now we need to move it over to the memory of our target process. So we already kind of know how to do. We will use virtual allocx and write some things there. So let's see. First, size underscore t shell code length is like Caesar of my sc. In principle, we could also try to be smart and just say that we only want as much as we used. So it would be sc, no, it would be code pb minus sc. But here let's just keep the whole block that we've created. Size underneath 10 m is equals shellcode length. Let's keep this approach. Shellcode length plus the path size plus of there we want a place for the null terminator, even though it's not needed. It's a nice to have. Okay, and then let's just copy our this thingy. It just takes length. Okay, now we need some addresses. Void asterisk dll path address is gleich byte asterisk address. But that's now address a process. So address plus shell code length void asterisk. That's all we need for now. Asterisk dll path ptr will be 64 dll path other. So now, oops. So now we saved this, as you remember, here, and now we are filling it in. Because while constructing the shellcode, we didn't know where in the memory, in the victim process, it will land. Of course, we could first do the calculations and then allocate the memory, and then we would already have the addresses. But this way, it is kind of more flexible, because we can grow the shellcode, and then at the end, we only set the few things we need to set, and it's completed. Okay, so write process memory process, comma, void asterisk, my shellcode, comma, then, comma, null, comma, oops, null has a type, okay. And then we write the other thing, dll, path, andere, comma, void Stern, andere, void Stern, dll, path, comma, dll path size plus size of this thing star, comma, null. Okay, and that's done. We return our address, and since we have, oops, and since the first thing is a jump to where we actually have our code, so this pdata thingy here, as you see, zack, here we set the that's the wrong value. Where did we save this? Where did we save that? We have a jump, p data size, jump bytes. Here we have it. So we are jumping by the amount of bytes that the data size is large, minus something, which we then here, after we're done with the data and entered our start code, wait, what do they call this finish code here? Data size, we should not overwrite. No, the data offset per byte. Quite sure if this line is correct. No, it's not. This should be there was a copy and paste error. That's the finish PTR here, I think. That must be the finish PTR here, because here we are the finish code and our no data size here, it's correct. No, it was fine. Then the label here is wrong. Main code. Yeah, that's fine. Main code, data size, and here's the finish code, which has its own pointer. This is a bit inconsistent, but let's leave it as is. Right, it should work. We should try it out. So do we have other breakpoints? So we will run it. Okay, it complains somewhere. Right. We have the wrong type. We need to make a cast. It should be fine. Okay. Or not. What's wrong there? Finish PTR is still 0. Finish PTR should not be 0 from the get-go. Yeah. Let's not use that. We will comment this out and not use it. We don't need it for now. We have not assigned it a value, and we are just continuing from the code to the finish code without doing any jumps, so we don't need it at all yet. Okay. That probably left a couple started but not resumed processes. Yeah, let's clean them up really quick. Okay. Debug attach to process. Hook test attach. Okay. Continue. And we end up first in the do debug break. And then we end up at some address in a breakpoint. And this is, when we compare it, where are we? Our code, it should be so, where is the main? Well, first we have our here breakpoint, and then we have a jump. Right, so we have a breakpoint, we have a jump, we have the two knobs, and then here, if we take the address and put it in the that's the wrong one. Here. Then we'll see some code, and further down we should see the path here. So it's definitely a code block, so let's follow it. So we make a step. Should be able to step over this thingy. Search violation, that is not good. Is this not a valid address? 1D. Let's see. No, it's here. C9 push. That should be fine. And this one should be not relevant. Let's quickly restart it just to see if we broke something. Okay, the thing is terminated. Let's run it again. Debug, attach to process, attach, continue. Okay, so here we are in the built-in break. It's also a C9 as you see, and we can resume from it. Now we come to our own break, and now we should be able to step. But we are not, so we broke something. What did we break? This should jump to 30 20. I think we are jumping to the wrong offset, that's why it doesn't want that. Although it's reporting the error too early. That's annoying. This one seems 90 0 0 1 2. But this is shifted wrong. We should have our there is some alignment error in this code. Let's see what's wrong. So we have our code. Let's add a few knobs just for a better trackability of the code. Right, this is terminated, or is this thing around? Right, this is that. Okay. So we have here a plus 40, and now let's add some knobs. Just a bunch. And we might have an alignment problem that we need to align correctly. But 40, we want to like 48, so let's go with 2, 3, 4, 5, 6. That should not be a problem. But add knob should be good. Let's try that out. Bug. Attach to process. Attach. Continue. Continue. Okay, so this one tells us now to go to 37. 37 is correct. Looks like it's correct, but it's right. This always worked. Why is this broken now? 37 is the right address. It's here where we want it to go. One breakpoint there. Settings. We said default. I mean, we could in principle just comment the breakpoint out, but CC, yeah, CC. But that should not make a difference. And then we just run it and see if it actually behaves as it should, but it did not. So something is... we broke something. Something is not yet quite right. It's probably some trivial mistake, like a small typo somewhere. Oh, sure, I know what. I screwed it up here. We need here execute permission. Page. Page. Execute read write. I mean, it's executable code. That's why it said access denied. Access denied. But now we should also we should clear that and switch to enable the breakpoint again 1. Okay. Is this thing running? No, it's not. Okay, let's run it. Good. Debug. Attach to process. Attach. Do we have the breakpoint here? No, we don't. Let's re-add it for now. Let's continue. Where are we? That's the built-in breakpoint, and that's our breakpoint. Okay, let's try again. Step. Yeah, now it's working. Step. Now we save everything. Step, 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 step. Prepare the call stack. So let's see. R9 should contain our Unicode string. So where is it? Command window, implement window. So let's see. R9. Let's say it's a short. That must be a pointer to a short. A pointer to a short. Nope. Wait. This points there. Let's go there. Just go there. Zack. Okay, so we have the length. There's something. That's the wrong one. We need the R8. Sorry. R9 is where we will write the thingy. It also doesn't look correct. I think we have another bug. If this will crash, this will very likely crash right now. Yeah. Arguments here are not correct. Let's see. So this one should be fine. This one's also looked fine. The path base. This is here and there. This helper correct. Code. Data PTR. Is this correct? Data PTR. We saved this value correctly. We did. And then what did we do with that? Yeah, because we just want the database. That should be correct. And then we need to plus here. Oops. Not the minus. Debug, attach to process. Zack, zack. Continue. One breakpoint, second breakpoint. Let's put the breakpoint here. Run. Let's remove it. Right, let's try again. So R8. Yeah, that's correct. 78 and 78, that's correct. It looks correct at least. The other one will be just pointing to towards zeros, which it does. So if we now take R8, then we make plus 8. This will be this one pointer. R8 should be the thingy, the Unicode path, and plus 8 like this, but that is not quite right. Yeah, that's right. It works. We have here our path. Oh, the path is not quite right because this is a Windows path. I think the function wants a NT path with a path with a different prefix, basically. We will try it as is, and if it doesn't work, then we will change the prefix. I don't remember exactly which notation this thing wants. Damn it, we forgot a breakpoint here. Also, since it crashed, it probably is still not yet bug-free. Debug, attach process, DLL hook, attach, breakpoint here, and here, and breakpoints. Okay, continue. This is our code now. We go to the call. Here, step. It worked. It loaded the hook. Then go to this jump instruction here to see if that one will behave correctly. Continue, okay. Then we make step. Where are we? Okay, that looks correct. But we broke something. Something crashed. So our code injection worked. Just the resuming of the original execution flow did not. Let's see what's wrong there. Sure, this needs a plus here as well. Yeah, I typed first minus and I just propagated the error multiple times. That's how such things happen. Attach to process. Attach. Continue. It's still broken. It is still broken. Let's see why. Okay, so we have here our last jump, database, return address offset, which should be here the return address. That looks right. Let's see. Data plus, and then the thing. It should be correct. Let's put a breakpoint before and run it. Damn it, I forgot to attach again. Run. Debug, attach. To process, attach. There is a Visual Studio extension which allows you to automatically attach to child processes, but it uses code injection on its own, and we wouldn't want that if we are doing our own code injection for fun. Okay. Right now it's already at 0. It did not trigger our... it did not trigger this code line. There might be some other issue before this happens, but in principle, so we have our call, and then we just restore the stack point. Let's step by step through it. Debug, attach to process. Apparently, probably it's a simple typo somewhere, but we never know. Okay, so we are here. Now we step over, zack, 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 or we can step out of those things. Okay, step. Okay, and then we pop all the registers except RSP, then we pop, and it looks correct, and pop FQ. and then we jump to whatever lies at this address, which is 1, 2, 3, 4, which is this. If we reverse it, 0, 0, F, and we need to get rid of the spaces. 0x. Thread seems the value seems correct. Okay, so step, 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 step. Okay. If we continue, it still crashes. We broke something. I'm not quite sure what. I mean, obviously it tries to jump to location 0. We might have something. It looks like that stack. The thread context is somehow broken, but it shouldn't be. Context control, is this correct? That's 64-bit, is also correct. Let's quickly check if this is correct here. Just the compiler is there, but then we need to change the order again. December add rsp 83. Do we do it in the right order? So we need to do it in the reverse order. So first we push this, then we push that, then we reserve stack, and then we unreserve stack, pop that, pop this. That looks correct. There must be somewhere some error. Since we are quite flexible in this code design, what we can do is we can comment out a portion of the shell code, so not do anything. We just save everything and then unsave everything. Let's see if we can find the error this way. Attach to process. Attach. Continue. Okay, so this is the default breakpoint. Now we have our breakpoint. And then we put a breakpoint here. Sub add pop push. Copy and paste error. I already see what's wrong. This loop of course needs to run in reverse. It needs to start at 0x0f. I must be greater equals 0. And this must be I minus minus. Because I said we need all the instructions to be now in reverse order. And the loop then of course needs to be inverted as well. We lost our breakpoint. Debug, attach to process, attach, continue. So we have a debug breakpoint, we have our own breakpoint. Now we get, yeah, it works. The thing is, if we don't attach our int, our CC int3, our CC will always crash the application. So now we comment this out, we leave the knob in place. Now when we run it, we achieved code injection. And since we only have a few minutes left, I think this is a good point to stop the lecture. This whole thing here could have been made significantly more complex, so we could have added some error handling, show an error message. We could have added the ability to actually call a function on the loaded DLL, so make it much more precise and other things. But in principle, it is just an exercise on what we already do here. We would basically just take this base offset value and then here call another function. In this case, if for example get procedure address, or on the NTDLL LDR get a procedure address, which would give us then an address of one function which is named. For the name, we would then again use a NT style string, just that it would be a 32-bit string for the name, so it would be basically the same, but would contain an ASCII string instead of a white string. And then we would get an address of the function as a returned value, and then we would just call the address once we're done with obtaining it. And then of course we could make it even more sophisticated. We could add a data field where we could pass random arguments to our function, which we call on the DLL. But all those things are not necessarily required. And here, for simplicity, since we don't have any more time, I think we will just stop at this basic example. If you are interested in a more verbose example, write me an email and I will upload something more complex to the Moodle as well. For now, I will just upload the recording of this last lecture and this code. Yeah, you have now still 2 weeks. So the next week is a holiday, so there won't be a lecture, and there is no lecture planned for the last week of the month. So this was the last lecture, but you have still over 2 weeks time to finish your final project in time. And if you need more time, then just write me an email that I know that you will submitting it late. Then this is absolutely not a problem. So I'll say it like this: if I don't submit all the grades, I think after 2 weeks or so, I will be start asking why they are not done. So just ideally you should be done with your final project in the first 2 weeks of the next month. Then everything is fine. If you need substantially more than 2 weeks overtime, then it would be good if you have some good excuse. But as said, it's not strict, so don't worry. There are no negative points for submitting it late. And if you have any questions, if you have problems with the final project, you can email me as well at any time to get some additional advice. And as I said, I think in the first lecture, it's important to be able to test your own code. So when you will be submitting your final project, keep in mind that you should also provide test cases for all the features that your code has, so that it can be easily validated for correctness. Yeah, and that's it. So have a nice exam season and a successful one at that. And have a nice weekend if you are already starting into the weekend. If not, then have a nice Friday. Bye bye.